it going, everyone? Mr. Geyser here with the final video in our Lesson B series, where we're taking a look at example 7 and example 8, where in this first example for this video, we'll be taking a look at the natural log function. Where in general, I know all of you know that the log function with the natural base of e is just defined as f of x equals natural log of x. Where really we're just saying that it's log base e, x, is equal to that natural log of x. We can just write that out right up here. That natural log is that ln of x, which is equal to log base e of x. We can plot that here up onto this board, where we now have these three main points on our graph. That first point down here being that 1 divided by that base of e, comma negative 1. That second point there being 1 comma 0. It still follows that base log function, where it passes through that 1 comma 0 point. And that third point there, which is just e, comma 1. Now, in general, remember that e is just some really fancy number, just like pi. E isn't a variable. E is a number. It is that 2.7182 blah, 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 right? So really, we're just taking a look at this y function, where we want to, this y graph, where we want to take a look at our f of x function, where in example 7, f of x is equal to negative 2 times the natural log of x plus 1. Where in part A, we can specify that the domain of this graph is going to be negative 1 comma infinity. This negative 1 here is being caused by this horizontal translation inside of the graph. Notice what will happen based on this negative 2 on the outside of our log. It's not going to change our domain. A vertical translation, negative or positive, a vertical dilation, negative or positive, is not going to affect our domain. Again, vertical dilation, vertical translations do not affect our domain for these log functions. But if we do take a look at that negative 2, it is going to cause some issues. That negative 2 there is going to be a reflection about the x-axis and a vertical dilation of a factor of 2. Really, we can write a rule for this that describes that our original points, x comma y, are being transformed into x minus 1, coming from that plus 1 up there, and y being multiplied by that negative 2. So keep in mind these three original points that we once had. All we're trying to describe is that these points are transformed on the graph here. Specifically, if we take a look at this first point here, for that first point, the thing that's happening is that this y x1 point originally was 1 over e comma negative 1. Now our x value is being subtracted by 1, and our y value is being multiplied by negative 2. And we get 1 over e minus 1, that horizontal shift to the left, comma positive 2. So all of these negative values down here are going to be flipped into the positive realm of our graph, and vice versa. All of these positive values are going to be flipped into the negative realm. We take a look at point 3 real quick. We're going to skip ahead. For point 3, y x3, it once was e comma 1. Now it's e minus 1 comma negative 2. Kind of the reason why we skip 2 is it doesn't really change. It has that vertical translation there. For all these points here, I want you to feel comfortable to do those reflections first and then those translations second. Think about what happens to the y values for this graph and then how it shifts. Really, to go back to the problem here, though, we want to take a look at part C. For part C, we want to state the range and the asymptotes, if there are any, there is one, of the graphs here. What really we're going to describe that asymptote is, it once was x equals 0, is now shifted 1 unit to the left from that part there. It's now x equals negative 1. And our range, though, is still the same. Our range is still negative infinity to positive infinity. And we want to describe our range from the lowest number to the largest number. Even though it's going from the positive infinity down to the negative infinity, we still write our range from the lowest number to the largest number. Now, in part D, we want to try and state any intercepts. We only have one intercept in this function here, where it happens to cross the origin. but also it crosses the y-axis. Whenever we have a graph crossing the y-axis, we know by definition that x equals 0. So really we're just trying to find the function of of x equals 0, so the function of 0, which is just equal to -2 times ln of 0 plus 1. Now, if we simplify out to get ln of 1, ln of 1, or the log of any base of 1, gives us 0. As a reminder, log base b of b gives us 1. If you take the log of some number and you have that as the base, you get 1. However, if you have the log base of anything of 1, you end up getting 0 as your answer. And -2 times 0 just gives us 0. In part E here, it asks us to state the function behavior and its concavity. In general, for this graph here, the graph is going to be going downwards at some kind of rate. For this graph, we're going to state that f of x is decreasing at an increasing rate, and it's concave up. In general, it's really easy to see that this graph is concave up, and it's really easy to see why this is a decreasing graph. It's starting up high and it's going downwards, but many students might still feel uncomfortable describing this at an increasing rate. Really, what I want to try and say is, let's just look at B. Let's just look at the blue graph. If we were to describe the rate of change of these two slopes here, that first slope being this maroon one, that's around like -2.5, and that second slope being -1.5, notice how we're increasing between these two slopes. So we'll always have an increasing rate of change for this graph here. However, because there is no inflection point, meaning the rate of change isn't going to change, that means for all of these ROCs continuing down, we're going to go from -2 to, -2.5 to -1 to -0.9 to -5, all the way down to -0.0000000000001. They will always be negative. They're always decreasing, but they will always be increasing. They're getting larger and larger, but there's still going to be some negative value because the function will always be decreasing. Keep that in the back of your heads for our next example. For this last part here, for part F, we're going to try and use that limit notation to describe that end behavior. In general, it's kind of easy to try and spot what the end behavior is for this. For that left end here, we're going to say the limit of x approaching -1 from the positive direction is approaching infinity, f of x equals infinity, and the limit of x approaching positive infinity, f of x is approaching -infinity. I want to explore why these limit notations kind of flipped around based on our previous function, where really the -1 is coming from the fact that that +1 there affected that vertical asymptote. And these infinities have switched around because of the negative vertical dilation. These infinities switched because it once was going down to -infinity as x went to the left and positive infinity as x went to the right. But since we reflected it about the x-axis, they happen to also reflect. Now, let's take a look at our next example. In example 8 here, example 8 states that g of x is equal to the natural log of 3 minus x squared, where x is any number that is smaller than 3. So right off the bat, we should feel pretty confident that we're looking at the negative side of this graph, which means there's going to be some kind of hidden reflection about the y-axis inside of our log here. In part A, we want to try and find the domain of g. But first, I do want to try and plot that normal f of x here, that y function that we're very familiar with that natural log. We're going to make it pink so it's a little bit easier to stand out when we use black to describe the rest of our problem here. The domain really is just being affected by anything inside of our parentheses here, where we want to try and state that this f of x, or this g of x, is equal to the natural log of 3 minus x squared, which is the same thing using that power rule of g of x is equal to 2 times the natural log of 3 minus x. But we want to try and state this 3 minus x as some type of distribute, right? We can pull out something to make it a distributed product rule, where we get this g of x is equal to 2 times the natural log of negative 1 x minus 3, where we're pulling out a negative 1 from both of these terms here. And now we're able to see that that negative 1 there is going to be the source of all those negative x's, where in blue is that vertical dilation that we feel pretty comfortable with. And it's going to be a factor of 2. And in red, it's going to cause that reflection about the y-axis. And in green, it's going to cause a translation of 3 units to the right. However, keep in mind that these two things, the reflection about the y and the translation of 3 units, are the only two translations that are going to affect the domain. That vertical dilation does not affect it. For the domain here is going to be negative infinity to positive 3. It's now negative infinity because this graph is reflected over the y-axis, and then it's shifted 3 units to the right. That's where the 3 comes from. In part B, we're asked to graph g of x here. When we graph g of x, we end up getting this kind of graph where it's reflected about the y-axis and then shifted 3 units to the right. Now, we know 2 points here. That first point happens to be that x-intercept. That x-intercept is really easy to find because those y values that cause some vertical dilation there are just canceled out. We're just looking at the x value of 2. That first point was 1, 0. It gets reflected about the y-axis to negative 1, 0. It's then shifted 3 units back to that 2, 0. We also know what that y-intercept is. We know that y-intercept is going to be 0, 2 times ln of 3 because that's just the equation solved when we plug 0 into g of x. When we plug in 0 into g of x, we get 2 times the natural log of negative 1 times 0 minus 3. We get 2 times the natural log of negative 1 times negative 3, where really g of 0 is just equal to 2 times the natural log of 3. Now, we can solve this out to some decimal value, but we can just leave it out as this here to make it a little bit more visual. Now we're able to move on to part C, where it asks us to state the range and the asymptotes of this function here. Where for the range, it's still that positive infinity to negative infinity, and that vertical asymptote is shifted from our 0, 0 to 3 units to the right. Notice that that vertical asymptote doesn't change based on the reflection. It just gets shifted 3 units to the right. So that vertical asymptote really is just affected by that red portion, or by that green portion here of that horizontal translation. Now we want to state any intercepts we have. Well, we already solved that. We have those 2 intercepts. We have that x-intercept at 2, 0, and that y-intercept at 0, 2 natural log of 3. We now can describe the functional behavior and the concavity. I want to pause here real quick. Make a guess. What is the function's behavior for g of x here? Is it increasing at an increasing rate, increasing at a decreasing rate? Is it decreasing at an increasing rate, or is it decreasing at a decreasing rate? Make your guess. Have it in your head. I'll show it in 3, 2, 1. Did you get it right? This g of x is decreasing at a decreasing rate. It's really easy for us to see that it's concave down. For us to see this decreasing at a decreasing rate, we're going to remove all those graphs there and just look at these rate of changes. Where for this function here, that maroon line is a very shallow but negative rate of change. The negative rate of change comes from the fact that this is just a decreasing graph. Right? It's decreasing over time, and it's going to be a negative rate of change. Then we go to that red graph, where now it's a more negative rate of change. Then we go to that orange graph, where it's a more negative rate of change. And then we go to that yellow graph, where it's an even steeper negative graph. And we are decreasing. We're becoming more and more negative for our rates of change. So the graph is decreasing at a decreasing rate. Now let's just take a look at our end behavior here for part F. We're going to use limits to state the end behavior. That left end behavior is going to go off into our positive infinity, where we have the x, or the limit of x approaching positive infinity for g of x equals infinity. and the limit of x approaching 3 from the negative side for f of x is going to approach negative infinity. And I want you guys to notice where these negative infinities and this negative part of the 3 come from. What's really happening is that because of the reflection about the y-axis, these two things here get switched based on our parent function. And this 3 here is being approached from the negative side because we're coming from the negative side from that reflection. And we're going to negative infinity from our left-end behavior because that's where x is approaching to the left. However, for the right-end behavior, our x is approaching 3 because of that shift in that horizontal translation. Thank you very much, everyone, for joining me for these videos on Lesson 12, and I look forward to seeing all of you guys in class. Take care.